All right, in 1.8, we're going to start talking about modeling, which is really the heart and soul of why we look at functions, to model real-life situations. Now, you'll see some real-life context in your homework. In these two examples, you won't, because this is just kind of replicating the skills that are going to be needed in your homework. Particularly the second example is really going to be the exact same, but just thrown into a particular context. But before we get to that example, I want to take a minute to talk about something from the quadratic formula called the discriminant. Okay, b squared minus 4ac, you may recall, it is the part of the quadratic formula that's underneath the square root. Okay, has some significance because it tells us how many x-intercepts that particular quadratic has. For example, if b squared minus 4ac equals 0, we know that that particular graph has one x-intercept. If it is greater than 0, it has 2. If it's less than 0, then it doesn't have any. Okay? Those are the three possibilities, and if you were to look at quadratic graphs with their parabola shape, okay, you would see that that's all. You can have 0, you can have 1, you can have 2. There's no way to take this U-shaped parabola and give it 3 x-intercepts. Okay? So applying it to this example, 4 squared, which would be 4 is b, minus 4 times a times c would be 16 minus 64, which would be negative 48. Okay, now without even looking at this graph at all, or even looking at the equation and thinking about its shape, I can tell you it has 0 x-intercepts. Okay, it does not touch the x-axis at all, meaning its graph would be something along the lines of an upside-down parabola that's below the x-axis. Okay, I can tell it opens down. It has a y-intercept that's below the x-axis, and doesn't have any x-intercepts. All right. If you see the term discriminant, that's what it's referring to. The reason we look at that is it's another little piece of information that can tell us some information about a graph. Okay. The next piece down here. All right. What I'm after is I want to come up with the equation of a quadratic in standard form with 3 unique pieces of information about the quadratic. 3 points. Okay. This idea is not new. We did that in 1.7 a little bit, where if we had the x-intercepts, we could go right to factored form. And if we had the vertex, we could go to vertex form to kind of jump to the equation. This case is a little bit tougher because I don't have any key points. Okay, I know this graph goes through the point 1, 4. I know it goes through the point 212. And I know it goes through the point 446. Okay, that's all I know. And none of those points are key points, which is tricky. Okay, we call key points. We call them that for a reason. They're helpful. Okay, they make the process of coming up with a quadratic model easier. All right, these aren't key points, so what I have to do here is just use the information that I have. Okay, for example, if I were to take this first point, 1, 4, I could plug 4 in for f of x. I'm going to actually start with the one on the far right. If I put 46 in for y, I could put 4 in for x, which would give me 16a. 4 in for x here, which would give me 4b. And of course, c is the constant, and it has no variable attached to it. Now, at this point, this equation doesn't do me anything because I've got an equation that I could solve, but the problem is I have 3 variables. For me to get this equation, I have to find a, b, and c. And I've got a totally valid equation right here, but I have one equation with 3 unknowns, which is a problem. Now I have a second one. I could put in 12 for y, and then put in 2 for x, so that would be 4a. The 4 is coming from 2 squared, plus 2b, plus c. I've got a system, and we've actually practiced already this year solving a system of 2 equations, specifically a system of 2 lines. These are actually going to end up being linear equations because they're, right now, a, b, and c are all raised to the first power. But 2 equations, 3 variables, still no good. Okay, that didn't work. If y is 4, I'd have 1 squared times a plus 1 times b plus c. Okay? Now, we got a lot going on here, but this is actually doable. We have 3 equations with 3 variables. All right? I'm not saying it's going to be pretty, but this now is a problem that is doable. It is mathematically possible to use this information to solve for a, b, and c. Okay? First thing I'm going to do is reduce this down to 2 equations with 2 variables. And I can see if I subtract these first 2 equations, I can already tell from looking at them that the c's are going to cancel. So 46 times, or minus 12 is 34. 16a minus 4a is 12a. And 4b minus 2b is plus 2b. Okay? I got that down to an equivalent equation that has 2 variables instead of 3. It's still not solvable because that equation by itself is just, one equation with 2 variables. But it's progress. I'm moving in the right direction, and it's really going to start looking good because I'm going to do this again with the bottom 2 equations. If I subtract those c's are going to cancel again. And 12 minus 4 is 8. 4a minus a is 3a. And 2b minus b is b. All right, so I've got a system of 2 equations now with 2 variables, which compared to solving 3 equations with 3 variables, I'm looking pretty good. Okay, I've got it down to 2 and 2. This is going to need a little bit of work to solve. I'm looking over here at the b's, and I'd like to multiply everything by 2, which would make this 16 equals 6a plus 2b. All right. Now I can already tell 2b minus 2b. That's going to cancel. 34 minus 16 is 18. And 12 minus 6 is 6. All right, now I've taken all this down to 1 equation with 1 variable. This is my kind of equation. 18 equals 6 times a. Nothing to it. Divide both sides by 6. Well, there we go. A is 3. I'm really starting to move in the right direction here. I know that a is 3. I'm going to move this down a little bit because I need some more room. I'm going to go back up to these equations in red. And now I'm going to solve for something else. And I'm going to take 8 equals 3a plus b. That looks like the easiest one to solve. So using this information now, I can say that it should be boxed off to keep this work separate. 8 equals 3 times 3 plus b, which means 8 equals 9 plus b. Going all the way down to the bottom here. Subtracting 9 from both sides, b is negative 1. Okay. B, so I've got a, I've got b. Now I'm going to go back up to this bottom equation here in blue, and I can say that 4 equals 3 minus 1 plus c. Okay? I found that a is 3. B is -1, and now I'm looking to find C. All right. Oh, 3 minus 1 is 2. Oh, then I can subtract 2 from each side, and C is 2. All right, down here in the bottom corner. Like I said, there's a lot to this. And again, the reason there's a lot to this is the 3 points that I've been given are not key points. This is easier if I was given the x-intercepts, because I could use factored form to make this much more efficient. If I knew the vertex, I could use vertex form and it would be much more efficient, but these aren't key points and it makes it tougher. Okay, makes it a lot more work. But I have reached my conclusion here. This would be 3x squared minus x plus 2. Okay, this quadratic equation right there meets the criteria as all 3 of those points that were listed are solutions to that quadratic. Okay, you'll have a problem like this in your homework, and then there'll be one other one that we'll throw at you where the process is the same, but the information, the x and y variables, have a context to it. I believe the example is looking at relating the amount of wheat planted in a field compared to the yield that farmer would get based on how much was planted. Okay, and the 3 pieces, the 3 points are just 3 random pieces of information about, if this much wheat is planted, here's what the yield would be. Okay, that's all for 8.1. We will continue modeling in 1.8, day 1. We'll continue modeling in 1.8, day 2, looking more at real life context.